In this video, we'll practice using L'Hopital's rule to evaluate some limits related to the function x squared minus 4x over 1 minus e to the 2x. The first limit we'll take is the limit as x approaches 0. You should begin by just trying to directly evaluate the expression by plugging in x equal to 0 in this case and seeing what we get. I'm going to put it in quotes because it may fail. We may run into some arithmetic problems, but in fact if I plug in x equal to 0 in the numerator, I'll get 0 minus 0. And if I plug in 0 into the denominator, I'll have e to the 0, which is 1, so I'll see 1 minus 1. And in fact, we get a nonsensical expression, 0 over 0. This is what we call an indeterminate form. Both the numerator and the denominator are approaching 0, and what happens to the ratio of those two expressions is not clear. It's important to keep in mind that as x approaches 0, neither of these functions are ever equal to 0. We're not dividing by 0 at any point. We're looking at expressions that are approaching 0, and it really depends on how rapidly the numerator and the denominator both approach 0 to figure out what happens to the outcome. Luckily, we have L'Hopital's rule, which helps us evaluate expressions that are in this indeterminate form 0 over 0. And to do that, what we do is we take the derivative of the numerator and we compare it to the derivative of the denominator and take that limit instead. And L'Hopital's rule says this will agree, it will be equal to our original limit. So carrying out the derivative here, I'll do the denominator first. The derivative of minus e to the 2x gives me minus 2e to the 2x. Don't forget the chain rule when you take the derivative. And in the numerator, we just have a polynomial, and the derivative of x squared is 2x, and then minus 4 is the derivative of minus 4x. We now have a new expression. Let's simplify that expression. And let's try to evaluate it by plugging in x equal to 0 again and see what happens here. And in fact, when I plug in 0, I now get a sensible arithmetic expression. I have minus 4 up top, and I have minus 2 times e to the 0, so I'll have 1 for the e to the 0, and this is a perfectly sensible expression. This function that we are looking at in this limit is in fact continuous at x equal to 0, and we can get its limit by directly evaluating at 0 to get 2. Let's look at another limit related to the same function. The only thing I'm changing now is letting x go to infinity. I'm going to look at each expression and analyze the numerator and denominator and see what the form of the expression is. And what we're seeing in the numerator is a polynomial going to infinity. In the denominator, I see a growing exponential function, and because of the minus sign in front of it, is giving me minus infinity for the denominator. So I'm looking at a ratio of expressions. The numerator is going to infinity, the denominator is going to minus infinity, and what happens to that ratio really depends on how big they are relative to one another. This is another kind of indeterminate form. Luckily, L'Hopital's rule can help us evaluate it. To do that, we look at the limits of their derivatives. I'm going to take the derivative of x squared minus 4x, and as above we get 2x minus 4. And the same limit that we did above, when I take the derivative of the denominator, again I get minus 2 e to the 2x. I now reassess the limit that I have in front of me by considering what happens to each as x goes to infinity. This linear function is growing, so it goes to infinity. And the denominator is still going to minus infinity. And so we're seeing another indeterminate form. I'm going to apply L'Hopital's rule again. I differentiate 2x minus 4. That gives me 2 minus 0. And I'm going to differentiate the exponential again. That will give me another factor of 2. And I'll get minus 4 e to the 2x. I now reassess what I've got in this expression. The numerator isn't changing at all. In fact, it's constantly 2. The denominator is a growing exponential function, and because of the minus sign is going to minus infinity. And we have an expression here that is no longer mysterious. It is no longer an indeterminate form at all. If an expression has a constant numerator and a growing in size, at least denominator, that ratio has to go to 0. And in fact, this shouldn't be any surprise here. I've got a polynomial function, something of degree 2. That's going to infinity, and in the denominator I've got an exponential function going to infinity. The exponential function will do it much, much quicker than the polynomial function, and so it will grow more rapidly than the numerator, and the ratio should go to 0 in the end. Let's look at another limit related to the same function. We'll look at x going to minus infinity now. When I do that, my numerator is a even power polynomial, so it will go to infinity as well. And then the denominator is now seeing the decay in the exponential term. That will go to 0, and I'll be left with the 1 here. So this will be 1 minus 0. This form here, infinity over 1, is not an indeterminate form at all. There's no mystery here what's happening. I have a numerator that's increasing in size, and then I've got a denominator that's approaching 1. And if I divide something very large by something pretty close to 1, I will get an expression that's still pretty large. And so the limit here will be infinity. I don't need to use L'Hopital's rule here, and in fact I shouldn't use L'Hopital's rule here. It does not apply to forms other than 0 over 0 or infinity over infinity like we saw in the previous two examples. So let's just conclude what we've gathered from these calculations here. We've looked at this function x squared minus 4x over 1 minus e to the 2x. Notice x is not equal to 0 because it makes the denominator equal to 0. We saw that as we go to 0, however, the ratio goes to 2, and that tells me right here that the limit will be 2, where we're seeing what looks to be a y-intercept. As x goes to infinity, we're seeing a limit of 0, and so we're seeing a horizontal asymptote along the x-axis. And as x goes to minus infinity, the limit is infinite, so we're seeing this growth in this direction here. Keep in mind, if I was to really zoom in right at what appears to be the intercept, we'd actually see a hole in the graph because the function is not defined at x equal to 0. And what we're saying by calculating this first limit here above is that there is a removable discontinuity at x equal to 0. I could easily fill that hole in and I would have a continuous function.